the zero effect. Suppose if it is a p-value in each term is the null hypothesis. So null hypothesis means it should have the low value. So you know the probability. So if the probability is less than 5%, so that means the null hypothesis is less than 5%, then the model is good. That means the p-value is less than 0.05. 5% means less than 0.05, then it indicates that it is okay. Suppose if p-value is almost 0, then your model is very perfect. Okay. Then the second one is R square value. So the R square value is higher. So higher R square value gives the good fitting of the model. So higher R square means, so you know R square is almost 1 means it is 100% fitting to the experimental data, your model. Suppose even if R square value is 0.95 greater than the 0.95, then the model is okay. So it is following good. Then the last one is the F value. So based on this F value, you can find the interaction parameters. As I said in the previous equation, y equal to x1 plus x2, x3, let us say x1, x2. Then x1 into x2, these two are the interaction parameters. Let us say x1 is the temperature, x2 is the time. So the combination of this, the product of this, you will influence. So that will be designed by this F value. So F value is high means your model is very good. So for a perfect model, so P value should be low and R square values and the F value should be high. So then the model is fitted well with the experiment. Okay. So next one is why to design the experiment. So why to use this design of the experimentation means to obtain the maximum information from the minimum number of the experiments. So as I said in the biological process, there may be 11 factors. So out of 11 factors, so please calculate 2 power 11. So 2 power 11 gives almost, it is more than the 1000. So to conduct such a huge number of experiments, it is very difficult. So in that case, you have to minimize the parameters. So by using this method. So then screening of the factors. So as I said, the screening factors are 11 to the, there are 11 factors. You have to reduce that 11 factors to 3 or 4, then it is fine. So you can conduct all the experiments. Then to get the exact fit of the actual model. So experiments has to be done such a way that the obtained data exactly. So please remember, because nowadays many researchers are using the design of experiment. So don't think that those fitted correlated model is helpful further investigation. So that is the only the screening purpose. After that, whatever the factors are influenced, with that factors again they are going for the simulation. So if the simulations are validated to that particular parameter, then the model is good. Okay. So the next one is how to conduct the experiment. So there are the several types of the softwares are available. Design expert software, Statistica, and MODI and DOE++ and StatSub and expert stat. So there are many types of Minitab. So one more design tool also will be available. So these are the software tools. So you can use any of these tools. You can find the optimum number of the experiments. So I have in my research I have used the design expert software to design the experiments. Okay, so that is very useful and easy. So what are the types of the experimental designs? So there are two types of the experimental designs. First, we have to screen the design. So these screening designs are especially used to find what are the significant variables. After obtaining the significant variables, then we have to go for the response surface design to find the optimal settings. So the response surface designs are especially useful for the optimal settings of the significant variables, significant factors. So in the screening designs, you have to find what are the most affected parameters, and from that affected parameters again you have to find the what are the optimal level of those parameters by conducting the experimentation. So these are the right side screening designs. There are uh, three types of the designs are there for screening the maximum number of parameters: two level factorial design and fractional factorial design and placket Berman design. So these are these three are the major one that can be helpful to screen the factors or the significant factors for the investigation on the response surface design. So in the response surface design, there are three level full factorial design or central composite design, so which is the most used tool for many process, and the next one is a box Benken model, and like that there are one more model is Dollard design. So now we are going to discuss the two level factorial design for screening designs and along with the placket Berman design, and in this response surface design, central composite design, we are going to see here. So in the full factorial designs, so it is comes under screening design. It can vary one factor at a time. So there is the screening design called OF80, one factor at a time. So that means if you have the three parameters, so you can fix the two parameters, then vary one parameter. So then you can observe what is the response or the yield of the process. Okay. So at a time you can vary only one factor. So it is not possible to vary two factors at a time. So then you have to perform the experiment for all the levels. So now let us say there are three factors, then you fix the two factors and vary one. And similarly you fix the another factor and another variable, then we have to vary one more. So like that you have to perform all the experiments. So then you have to combine all the interactions which are captured by the experimentation. So here how can you find this total number of experiments? This is the formula that can be used. N is equal to Ni. So pi of Ni. So that means if there are two factors, this is the product. So Ni. So N, let us say two factors, N1 into N2. So this, by using this formula, you can find what are the total number of experiments that can be designed. So now see the table here. This is the for three parameters. This is the table which shows 2 power 3. So that means here 8 experiments we have to design. Let us say three parameters are A, B, C. In the trial one, so it shows the -1, means -1, -1, -1. So you have to fix all this. You are not varying. So in the second one is -1, -1. You have to fix the two variables. Then it is varying. So like this, there is a varying of the parameters. Then you will get the 8 experiments. 2 power 3 is 8. So 8 combination of the experiments. Let us say this is the minimum value. So -1 is the minimum value and +1 is the maximum value. So you can design, let us say A is the temperature. A is the temperature. I'm considering temperature is a 50 degrees Celsius is the minimum and the maximum is the 60 degrees Celsius. So now I have to conduct the experiment temperature 50 to 60. Similarly, the second parameter is, let us say, the time. So time is, I am considering 60 minutes is the minimum and 120 minutes is the maximum. So now it is designed such a way that 60 or 120. So there is no intermediate value in this factorial design. So here -1 means it is minimum and time also minimum, and the third variable, let us say pH. Now I want to vary the pH, let us say 3 to and 5. So maximum is 5 and minimum is 3. So it is the combination. So 50 degrees Celsius and 60 minutes and pH is 3. So this is one combination. So like that you can get the different combinations of the experimental run. So for these factors. So please remember A, B, C are the factors. So for that factors you have to define what is the minimum value, what is the maximum value. According to that you can design your experimental runs. So the second one is the Plackett-Berman design. So the Plackett-Berman design is the first order polynomial equation which is given by y equal to beta naught plus sigma I equal to 1 to n beta I into xi. So as we discussed in the previous case, beta naught plus beta 1 into x1, beta 2 into x2 like that. So that is the case of the Plackett-Berman design. So in the Plackett-Berman design, so it is efficient screening method, as I said in the previous case. So it comes under screening design compared to all other process in the screening design. So Plackett-Berman design is the one of the useful tool to find the better significant variables. So this is the general expression y is equal to beta naught plus beta 1 into x1. You can use any equation. Here beta, in place of beta I used b naught plus b1 x1. So this is the regression equation. So when to use the Plackett-Berman? So whenever in the early stage of experiments you don't know what kind of parameters are more influenced, then it is possible to neglect the higher order interaction. So whenever you want to neglect the higher orders means, let us say x cube x power 4 time, then this Plackett-Berman design is used. Up to x1 x2 means up to x2 or x square you can use the Plackett-Berman. So more than this higher orders you can neglect those terms with the help of this Plackett-Berman. Then it can be helpful two-level multi-factor experiments. So when the number of factors involved is higher, then this is the best tool, and technologically detect the large main effects. Means what type of the parameters are used. This is the one chart that is helpful to find the most affected parameters. You know the Pareto chart. So this is the graphical chart that can be helpful for a quick decision on the selected parameters. So here there are the color indications. So here one is the blue color and the other one is the orange color. So orange color factors are more influential compared to the blue color factors. So like that this chart will show what the factors we have to consider, what factors we have to neglect. Okay, this is the main use of the Pareto chart. So now as you know, this is the biological process, citric acid production. So one of my published paper. So this is the table which contains the parameters. There are 11 parameters. So sucrose concentration, methanol concentration, and the inoculum density, and pH value, spore age, stirrer speed. So like that, there are the 11 parameters. So out of that 11 parameters, so conducting of the experiments for all the 11 parameters combination is very difficult. So that I have selected the low level and the high level values. So in between, so it will generate the combination of the experiment. So these are the combination after generation of the combination of the experiment. Then the experiments have done to find the citric acid concentration. Last column is the citric acid concentration for all the combination of these factors. So where the maximum, so this is the point. If you see here 67 grams per liter of citric acid is obtained for this combination of all these 11 parameters. Okay. So 11 or 12 experiments, it is not a difficult task to conduct. So that is why in the Plackett-Berman design is the screening design before actual conduct of the experiments. Okay, so now out of the 12 experiment, so the 7th run gives the maximum yield of the citric acid. Okay, so now the next one is the central composite design. So it is the important design which gives the response surface polynomial, especially in the quadratic expression. So this is useful tool. So it is a combination of the first order designs plus central and axial points. So you know the 2 power we have seen the factorial design. So 2 square or 2 cube. So it is combination of the factorial plus the central axial points. So these are the combinations of this. This diagram shows the combinations of the response graphs. So first one is fractional factorial design. Fractional means it is very small. You have to consider the small level, small number of the small factors only. Means small number of runs we have to. If you want to run a small number of the experiment, you have to choose the fractional factorial design. Now, if you want to run the complete experimental run, then you have to go for the full factorial. So this shows here only the 4 points. So here almost at all the points you have to consider all the factors. So this is the replication. Replication means duplicate combinations will come. And this is the central composite. So by combination of all these, the central composite design will be exist. So now what is the equation that can be used for the central composite design? The total number of experiments with full means you can go for the small scale design or the full scale design. Suppose if you want to consider the full scale design of the central composite, then you will get 2 power k plus 2 into k plus 6. So these are the combination of the experiments you have to find, you have to get. So let us say if it is a 3, so now 2 power 3 plus 2 into 3 plus 6. So these combinations of the experiments you have to perform. So let us say you have the factors temperature or the catalyst or the time. Now how can you, because it is a statistical tool, so that doesn't know what is the temperature or the time, then you have to assign that factors in terms of the coded values. So that coded values are designed with this formula xi equal to wi minus wi naught by delta wi. So that means let us say the example one temperature is 60 degrees centigrade is higher and 50 degrees centigrade is lower. So now we have to give the coded values. That coded values are range from -1 to +1. So in between 0 is existed. So how can you find this -1, 0 or +1? So these are the coded values. So let us take the example wi minus wi naught by delta wi, the same formula. Now we can use 60 minus 50. Delta w is the difference in this minima to the maximum. So it is 10. So now 60 minus 50 by 10, you will get +1. Suppose if you take this here lower values, so 50 minus 60 by this is always 10 only. So you will get -1. So like this, +1 and -1 are the coded values are given to the statistical tool. So then only the regression equation will be generated like this. So the quadratic equation is generated with this formula, which is obtained beta equal to alpha naught plus j equal to 1 to k alpha j into xj plus j is equal to 1 to k alpha jj into xj square. So if you observe here, this is the x term and this is the x square term and this is the combination of x, x1, x2, x2, x3 like that. Then you have to allow some error by using this formula for one of my research work. This is the case for methyl acetate production by using the reactive distillation process. So I have chosen the six variables. I have assigned the low values and the high values. Then the central values are obtained. So for this, the regression model equation I got. This is the square root. So square root means root of y is equal to this expression. So see here, it is a big equation in terms of the factor 1, 2, 3 up to 6. Then the combination of the 1 and 2 and 1 and 3, 1 and 4. So like that it will gives the total interaction of one parameter to the another parameter which are most significant. So means which are more influence on the yield of the product. So this is the plots which shows the goodness of the feed. So these are the predicted values and the actual values. Actual values means the experimental values to the predicted values from the regression model. So if you observe here, almost these two are linearly dependent. So here predicted and actual values are almost following in the same trend. So this is the another graph which is the outer T plot. So if the values are lying in between plus or minus 3%, then the model is very good. So these are the residual runs versus the number of experiments. I have done the experiments around 34. So out of 34, so even one experiment is beyond that plus or minus 3%, then the design is not suitable. So that means all the experimental runs should be under the plus or minus 3% for internally studentized residuals, then the model is fit. So it's a very good representation for indication of the goodness of the fit. So this is the RSM response surface graph for mole fraction of the methyl acetate versus the reflux ratio and the reboiler temperature. So here at a reboiler temperature of almost 70 to 80. So here if you observe here, so 75 degrees Celsius, then I got the maximum yield of the methyl acetate and the reflux ratio is around 1.8 or 1.9. So for that optimized parameters, I got the maximum yield of the methyl acetate. Okay. So this is the ANOVA analysis. So ANOVA analysis that can be tested as we discussed now based on the F value and the probability value, phi value. So if the probability value, if you observe here, this is the only partial parameters I have given in here. So if you observe here F value is around 395, means it is more than 100, it is a very good fit. So then P value is less than 0.001, so it's a very good fit. So that means already we have discussed if P value is less than 0.05, then the model is fitted well. Okay, so these two are the indications of the model fitting. Okay, so let us come to the conclusion. So design of the experiment, this is the useful design especially for screening of the parameters, mainly in the biological process where the maximum number of parameters are influenced on the yield of the product, then it is very useful tool. Then the minimal number of the experiments will be obtained with the help of the design of the experiment. So it can be applied for any type of the area. So it won't be for biological or chemical, or even if you consider any mechanical type of the design or the pharmaceutical type of the design, means where the product you want to get. So even if I saw many types of the applications are there for especially in the central composite design. So that means it is a vast area. This process can be applicable for all kind of the areas. Okay, that means you can find the interaction of the individual as well as the interaction of the combined variables. So mainly many researchers only they can find that only one variable is influenced on the yield, but the combination of the variables that cannot be given any type of the model regression. So in that case, this process will be helpful. Means the design of the experiment will be helpful, which parameter is more influenced on the design design process. Okay. So thank you all. So if you have any queries, you can ask.
Thank you, sir. Participants, any queries?
Thank you for your nice presentation, sir. Actually, we are also working using these particular design experiments. Normally, I use the box Bunken and, as you said, central composite. Okay, central composite we were using for the screening. So, can't we use the central composite for screening, sir?
No, madam, because as we said now, it is the combination of the 2 factorial. Already I have mentioned.
Yes, you said.
So, here, let us see this. Yeah, this is the combination of the 2 factorial design plus central actual design point. So it will, because this is a good question, madam, because as I said, in the CCD also there are small scale design and the large scale design. So you can choose the process if you have the more than 6 parameters. As I said in my one of my PhD work, I have the 6 factors. Those are influenced on the yield. So then I have go for the small scale design. Even that small scale design also gives the better models. So we cannot go for the screening for CCD.
Okay. Papers are reporting, sir, with the central composite, they are going for screening, especially fixing at 2 levels. So how about the validation of the design, sir? You have not done the validation of the design?
But I have not shown, madam. I have validated. So after getting this regression model, then yeah. So these are the ANOVA results. After that only, whatever the optimal points I got, then I have validated the experimental, because after getting the regression model, again we have to test the model by performing the experiment, but I have not shown here.
Okay.
Because this is one of the useful tool, madam, because wherever many factors are there, exactly it can be helped.
Okay. Yeah, how many, actually you have taken 11 parameters. See, you said that in your screening, in your this particular central composite, you said that you have taken 11 parameters, no sir?
Yes, ma'am.
Yeah. So in these particular 11 parameters, what are the dependent variables? How many dependent variables? It is only the citric acid content you kept as the dependent parameter?
Yeah, citric acid concentration, or one more response I can add, yield also.
Okay. So
we can have multiple responses also.
So how many you have taken
here? Response 1 and response 2.
So okay. So, but in this diagram for the plaquette Berman, you have only taken one particular response, that is citric acid.
Yes, ma'am. Yes.
Okay. So only citric acid you could keep as the response, and you have taken all these independent parameters.
Yes.
Okay.
Because as I said, 2 power 11 is very difficult, madam.
Yes, sir. It is 4 levels.
Out of 11, which are more influenced on the concentration, because the objective is the production of the citric acid, means high amount of the yield I have to get.
Okay.
So yeah.
So when I use this plaquette Berman, which type of results I do you got it, sir? Whether it is linear or whether you were getting a polynomial? And how to know that whether linear is good or polynomial is good?
Here in the
Because normally when we go through the papers, when we were only doing some responses we get in the form of a linear, some we will get in the form of a polynomial.
That depends on the process, madam.
Process.
That depends on the process. You can't say linear is good or non-linear is good. Suppose if linear is not fitting, then you have to go for the non-linear.
Okay.
Otherwise, sometimes some type of the works, even the non-linear regression will be converted to the linear expression with the help of some techniques.
Okay. Okay.
So I can't say that linear is good, non-linear is good. So our objective is you have to develop a model which should be having the R square value of more than 0.95. Then F value and P value should be as per the design.
Should be less and F value should be high.
Yeah.
Say for example, you have run this particular 11 experiments. Okay, you did not get a correct concentration of the citric acid. But using the same model, can we add some more some more experiments to that? If so, where we need to add? Can you show me that in the design of experiments in the software?
Yeah. So now whatever you are asking is, I'm coming to that example. Yeah, there are 11 parameters. I got this only 12 combination. Yeah. So can I go beyond this? This is your question, madam. Yes, exactly. You can go beyond this, but this is the screening. So after 12, it can shows what are the most influenced parameters. Okay. Most influenced parameters. So even if insignificant parameters, if you are varying, if that does not reflect on the concentration of the product, then why should I consider these parameters? Yeah, that is it. That I understand, sir. That we do in the screening. That is done. Okay. From the screening, I say that you have selected 3 important parameters which are affecting the concentration of the citric acid. Yes. Okay. Now these 3 factors, now you have taken it for the surface response methodology. Yes. Further detailed experimentation. Yeah. That's what we will do a further experimentation with the 3 factors, keeping at 3 level. You have run the experiment. You got the results. Yes. Okay. Now, after getting the results also from the given experiments, I say that the data is not fitting properly. So, can we increase the number of runs? Can we increase the number of runs? Runs, yes. Yes. We can increase the number of runs. Yes, sir. So, where we need to increase that particular number of runs? That you have to select the minimum and maximum values. Okay. Minimum and maximum values means, let us say now in placket Burma design, I have given temperature as a 50 degrees Celsius. This is the minimum value and maximum value is 60 degrees Celsius. Yes. Now, even though if my model is not good, then I can decrease the temperature to 40 degrees Celsius. Then it is increase the temperature to 70 degrees Celsius. So based on this, the combination will get. You will get the another combination of another set of the experiments. Okay, fine, sir. What you said is I totally agree. That is the question. Okay, that is. But again, see, we know that when we are using this particular model, we will also keep center points. Yes, madam. So, and we say that it is interday and intraday. Okay. So with the given number of parameters itself, with the given number of center points itself, with the given conditions, if the design is failed. So in that same design itself, I want to increase the number of runs, not varying the parameters. Yeah. Then you can add now I got your point, madam. Now what you are saying is, I got the only 3 parameters, 3 factors, right? Yeah. So for 3 factors, we have the combination of the experiments. Okay. So the combination of the experiments won't give the exact, it is failed. Totally the design is failed. Right. So now can I go for the another set of the experimentation? Yeah, you can go. You can go by taking, I think 3 level factor is there because I don't know exactly because I have seen this,
Sir.
the coded values are there, no, madam. Coded values +1 to -1. So there is one more factor we have to design, that is plus or minus 2.85 or something like that. So you have to account that factor into this coded values. Then that will give the another set of the data.
Okay,
Experimental.
experiments it will give.
Yeah.
That's what, with the central point.
Yeah, central point. So you have to go further. Suppose the coded value is +1, -1. In between center, obviously it is 0. Now, if we are not getting this set of data, it is failed. Then we have to go for one more set of data plus or minus 2.85 into this coded value. So that will give the another combination of the
Why only
parameters.
2.85, sir? Why only 2.85?
There is it is a statistical design, madam.
Okay.
Because even it is 2.85 something like that, because I am little bit confused, because
Okay, maybe, I don't know, because I have a doubt. Maybe you can answer me tomorrow also, sir, because if you are going to continue.
Yeah.
Other time also. No issue, sir. Because I know working with the designs, it's not easy.
Yeah. There is a factor, madam. Yeah, you are good. The question is good. Because for me, it is not the case happened.
Okay.
Within this limit only, I got the good model fitting.
Okay. Sir, even you are going to show us the trial run, sir? Not like this, running the design on your desktop. Can you show us?
Actually, I am busy, madam. Not busy. Thing is, I am doing some other works. So that is why.
No, because theoretically, see, everyone can learn theoretical aspects. That is good. But if you run the trial, of course, I know how to run the trial. We are working, but it's because I know design of experiments is always a learning process. So
Exactly.
if somebody shows some things maybe which I don't know, I can learn. That is the main thing. So if you can just, because already you have the design tool with you, if possible, can you just maybe today or tomorrow or in between, whenever your talk is there, 10 to 15 minutes of the demo of that particular run will definitely help the participants. That's what I feel.
Sure, madam, sure, but yeah, I will show.
We'll try to adjust the session, ma'am. Some of the days based on sir's schedule, we'll arrange, ma'am.
Okay. Please, I need to request you to give that particular demo, sir. Right?
Sure, madam, sure, definitely, I will.
Okay.
I will show the demo.
Yeah. Thank you very much.
You,
Thank you.
Thank you for the question. Thank you, sir.
Okay,
Are there any questions? Are there any questions, participants? So can we end the session?
Yeah.
Thank you.
Yes.
Thank you, sir.
Thank you, sir. Thank you.
Feedback link will be sent in this chat box only.
Okay. We don't have any other class now after this particular talk.
No, ma'am. This is all for today, ma'am.
Okay. Right. Thank you.
Thank you.
Sir, can I close this PPT?
Yes, sir. Yes.
Right.
Thank you, sir.
Thank you all.
Thank you, sir.
Thank you, madam. Thank you.
We'll be posting the feedback in the chat box and WhatsApp as well. Thank you, sir. Thank you for your presentations.
Okay, sir. Thank you.
Malay.